Good morning, everyone. I would like to welcome all to this webinar on monitoring MV and LV assets using LoRaWAN network. First of all, I would like to thank you, everyone, for taking time from your busy schedule and joining this webinar. To introduce, I'm Nirmal Thalil, looking after the energy IoT products in Calcutta. Energy IoT products includes Kalki.io, which is a cloud-based head-end system, as well as SyncConnect, which is an edge-based data acquisition software. So before starting the webinar, I would like to inform you that if you have any questions raised during the course of the webinar, you can type in those in the questions menu provided in the GoToWebinar screen. We will address each of your questions during the end of this webinar. If time allows, else we'll get back to you personally. So to start the webinar, so today's topic is monitoring of MV and LV assets using LoRaWAN. Today, we cover these agenda items. Let's start with what is an MV and LV assets monitoring. What are the types of loads connected at each voltage levels of MV and LV, and why this monitoring of MV and LV is important, and what are the business case and use cases of monitoring and MV as well as LV side. Then we can narrow down, we can see what are the different communication network options useful for the MV and LV, and why do we select LoRaWAN as one of the suitable option, communication network option for distribution network automation. Okay, so let's start with this. So this is a typical MV or LV network, distribution network, where we have multiple levels of MV network counted on different types of loads, like an industrial load or business complexes, and there could be multiple MV water levels depending upon the loads it get connected to, like small scale industries or buildings will be connected to a MV network, a low voltage MV network, as well as big heavy industries will be connected to a high voltage level. And on the LV side, we'll have the residential customers as well as small business enterprises and business stalls, etc., which would be mainly consuming a three-phase low voltage or the single-phase low voltage network. So why do we need to monitor an MV and LV side network? So basically, monitoring of MV and LV is required to ensure reliability and quality of electrical distribution. There are various indices like SAIFI, that's average number of interruptions faced by a customer. SAIDI, that's average outage duration faced by a customer during a period. Typically, it will be yearly value. MAIFI and KD. So there are various indices to indicate the power quality. Similarly, power quality side, we have TPQI, that is the total power quality indices, which is calculated from the power quality measurements like harmonics, interharmonics, voltage fluctuations, flickers, surges, sags, swells of the voltage, etc. So remote monitoring data and alarms from the system assets enable the utility to operate the network at a greater efficiency and improve safety and with a minimal number of power interruptions. So it also helps in network planning to get access to load and voltage data, and decide if any fine tuning to be done on balancing the load uniformly in the network, or where how much DER power can be connected at a given moment. So these are the various use cases which requires monitoring of MV as well as LV side. So there is some amount of automation done on the MV, but the LV side was totally ignored, and this has a huge gaps in knowing the exact these indices, um, which needs to be improved by the utility. Now let's look at some of the devices and data which needs to be monitored. Like for example, in the medium voltage, we have got fault passage indicators or line fault indicators, which shows the fault has occurred in the network. It could be a sectionalizer or auto reclosures, switch positions, or it could be an IoT sensors, it could be winding temperature, OSM temperature, or bus bar temperatures, or source sensors, pump temperatures, etc. There could be a feeder protection relay, which is obviously sitting in the substations, which looks at the protection of the feeders faults. So it also exposes a few data on the protection of the feeders. On the low voltage side, data needs to be taken from meters, especially it should be a power quality meters to monitor the supply voltage and current of each phases, maximum demand, load, LV feeder phase loads, harmonic current, voltages, total harmonic distortions, imbalances, etc. If any. And there could be switch positions on the LV side as well, which needs to be monitored, and also use this information from the calculations. For example, switch position is not available, or you can have I need to have some calculated logic to identify the switch position as well. So these are the typical devices needs to be connected, to be monitored, and data to be taken out to the central location. So in order to achieve this uh, objective, let's look at what are the typical communication characteristics required for monitoring a distribution network. So main challenges for monitoring a distribution network is it's been deployed on different geographic locations. Like distributions are deployed in urban areas or semi-urban or rural areas. So to make monitoring solution viable, communication network used for the MB and LV monitoring solution should be able to meet diverse deployment scenarios. So let's look at the requirement consideration for the selecting the communication network. So network shall be capable of communicating with the devices located in dense urban area with high-rise buildings, and shall also be capable of communicating with devices deployed inside the building, such as basement area, where you could see a small LV substation sitting inside the basement area of the building. And it could be for a semi-urban areas, there could be distance between the nodes would be much higher. For example, the feeders, distance between the distribution transformers would be much higher in terms of semi-urban and rural areas. And the number density of nodes is also very less compared to an urban area. Number of nodes for urban location would be higher. So network should be capable of communicating with a larger set of devices with a minimal infrastructure. Also, technologies used in IoT sensors are also improving significantly. So number of sensors which needs to be connected will also grow exponentially. So considering all these factors, we should have a communication network. We should sell the communication network to accommodate this growth. Another important factor is the cost. Overall cost of creating the network and maintaining the network shall be very minimal. Operational cost of network shall also be less or should be nil. So a preferable option would be a wireless communication network with, if possible, with an unlicensed spectrum, and shall be vendor independent solution with an open software is preferable for that kind of a scenario. And obviously the cost and effort for deployment of solutions shall be very minimal. So to support auto configuration on registration of the devices, it is recommended that the device automatically identifies the geolocation and use this info for network registration and hence the control center header. So automatic geolocation identification is also a critical feature of the communication network which needs to be available. So looking at all these characteristics, let's pick all the communication options which we have right now on network range versus bandwidth plot. So this is how it will look like. You can see that the plot provides a comparison study of network range versus bandwidth. So we see that both the Bluetooth and NFC and the wireless body area networks are less range, and bandwidth is also very less compared to other options. Bandwidth of Wi-Fi is much higher, but the range coverage area is very less for a Wi-Fi technology. But there are technologies like CP or wireless PAN, which is having improved network range, but that's also not suitable for our application, distribution monitoring of LV and NV side. So the few of the best suitable options would be the 4G or NB-IoT network. That is especially the cellular network, latest cellular network technology is one of the option, and another option would be the VSAT, and another option would be LoRaWAN or low power wide area network communication technologies. So out of these three, we can roll out VSAT considering the operational and deployment cost of the network. So we have the LoRaWAN and the NB-IoT. So let's look in details of these two technologies and what would be the best option for us to choose from. So LoRaWAN or other narrowband networks is compared with 4G options released. So we have got three releases of 4G, release 12, 13, and 13 plus. You can see that bandwidth offered by LoRa and other narrowband network is in kilohertz range, while 4G offers higher bandwidth. However, for distribution monitoring and higher bandwidth is desirable but not mandatory, especially for a low voltage network monitoring. So link budget of is higher for LoRa. That's around coming around 154 dB compared to 4G, which helps in larger coverage area and use a smaller number of base stations. Other important factors are the immunity, interference immunity, which gives immunity to other network interferences, and also the coexistence feature. We use LoRa and other edge in the comparison. So interference immunity is also higher, and it can also coexist with other networks using the same radio frequency. And let's look at the cost factor as well as critical for the MV and LV. So you can see that the cost of LoRa would less compared to LTE or NB-IoT technology options, mainly because the LoRa is using the unlicensed bands, ISM bands, but in case of LTE and the other cellular technologies, use licensed bands for the communication. In addition, the power consumption is also very less for LoRa and the low power wide area network communications. which also gives an additional advantage uh, over the cellular technologies. You can also deploy LoRa on public or private network. So network can be a publicly hosted network similar to a cellular technology, cellular service provider, or you can also host your own uh, private LoRa network uh, possible using this technology. So considering all these factors and comparative studies, so we find that the LoRa or low power wide area network would be a better bet for the MV as well as LV monitoring solution. So let's look at the details of LoRa and why LoRa would be a best option. So LoRa uses LoRa is basically a wireless communication. It uses a modulation called SHIP, which was used for military and space communication for decades and for long communication distances and robustness to the interface. It provides a long range communication up to 40 kilometers in rural areas and up to 3 kilometers in urban environment, and basically it depends upon the performance of the gateways used. It uses star topology. So the battery lifetime of each node is preserved to maximum and required to be utilized only when necessary, unlike a mesh communication technology. And the communications are also asynchronous. That means each nodes will communicate only when they have to the base stations. It could be on event basis or it could be periodically, but until and unless there is no communication data to be transferred, there will not be any communication happening between the nodes and the base stations. That is also a huge advantage in terms of utilizing the bandwidth for other nodes and other data to be transferred over the network. And it has got high penetration rate compared to other wireless technologies. Basically, it uses a mechanism called um, automatic data rate, is ADR. It's used to adjust data rate to suit the environment. That is, if a device is closer to a gateway or base station, then it will use less power, less time on air, and higher data rates. So all the devices closer to the gateway will communicate faster with the gateway on high data rate, which means that other devices which farther from the gateway will have more time to communicate. Similarly, end devices located for this point will use higher power as well and lower data rate. So with a lower data rate and higher power, it ensures that data from nodes from further point will always reach the base station, uh, which might have higher productivity. And it has got high network capacity. Basically, it is achieved by using multi-channel and multi-modem receiver in the gateway, so that simultaneous messages on multiple channels can be received in order to make an adaptive data rate work. Symmetrical uplink and downlink is required with even downlink capacity uh, closest to a gateway. Obviously, it has a multicast messaging, which uses minimizes radio congestion for low power devices. This feature is used for effective update of the firmware, massive device configuration, or synchronized device activations, or any emergency actions can be uh, issued using a multicast message. And other advantages is 2 to 3 times less expensive than traditional operator cellular networks, mainly because of the better coverage, and operates on a license-free and cost-free ISM bands. That's industrial, scientific, and medical bands, which is some specific bands which is located free for public use. And another feature is the geolocation. So unlike other cellular technologies, so there is a LoRa uses time differential on arrival and other hybrid techniques to determine the location without using extra processing power of the end devices. So automatically it identifies the location of the devices, which helps us in auto registration and auto configuration of the devices. So if we have the location and the other identities of the devices, we can automatically register a device with the header system, and we can push the configuration from the header system once we know that which device and from where it is connecting to. So these are the specific advantages of LoRa, which will be useful for a LV as well as MV monitoring applications. So let's look at the details of device classes in LoRa. So in LoRa, the devices is classified as three: Class A, Class B, and Class C. Class A is energy efficient devices, as for example, the battery powered sensors. Class B will be energy efficient with a latency control downlink. That is the best example would be battery powered actuators, where there could be some control commands need to be shown to the devices, but it's mainly battery powered. And there could be main powered actuators, which are devices should be continuously listening and have no latency for the downlink communication. So for the distribution LV side and LV monitoring, so also the devices has to be configured for the Class C devices. So this is the network stack of LoRaWAN. On the physical layer, it uses regional free ISM bands, depending upon each region. So the frequency used allocated are different. So there are standards which says what are the bands to be used for it, depending upon each region. And on top of that, there's a link layer. Is a LoRa modulation, that shift modulation techniques are used. On top of it, there are different device classes. In our case, it will be mostly the Class C devices, which we can also have issue commands as well to the devices if it is Class C devices. And network layer will be LoRa WAN network layer. And on top of that, you can have that application stack communicating over the LoRa, or if you want to transfer the normal automation and control protocols like the DLMS metering protocol, or DNP3 or Modbus, which basically uses an IP connectivity. You can use SCHC, that is static contest header compression techniques. So additional gateway or additional stack, which will be it needs to be integrated with the LoRaWAN network. So using SCHC gateway, you could basically run a DLMS or DNP3 or Modbus protocol over the LoRa using a compression and fragmentation techniques defined in the standard. So this is a high-level view of the network stack. To talk about the network architecture, so LoRa-based network nodes. In our case, it will be DT meters, or it could be a solar panel inverters, it could be a sectionalizer or capacitor banks, or small DT transformers. All these equipments is having the LoRa connectivity will be connected to a LoRaWAN network through a gateway. And LoRaWAN network can be directly connected with the head-end system. It could be directly integrated with historians or SCADA systems or DMS systems, DEMS or the ADM systems, which is available with the utility through a front-end gateway called Kalki. You can use Kalki IO for as a front-end gateway and connect the data, collect the data from the LoRaWAN network server and share it with legacy systems, OT systems, or the standard protocols like DNP3 or IEC 60870.104 or ICCP or even IEEE 2030.5, which is Sunspec Solar standard. If you want to share it with the DEM systems as well. So Calcio front-end gateway has got interfaces to connect with the LoRaWAN network server and take the data and give it out to the OT systems. If you want to interface with an IT or IoT network or systems, you can use MQTT interfaces from the front-end server and take out the data to the an IoT platforms like AWS platform or Azure IoT platform. For the devices which supports native protocols like DLMS, Calcio can make use of the SCSC gateways provided either by the third-party provider or it could be provided by the LoRaWAN network server as an additional stack to transfer the payload, communication payload like the DLMS or other application protocols over the LoRa using the SCSC gateway. So this is how the overall network architecture will look like. Okay. So with this, I would like to conclude the webinar on the LoRa-based MV and LV network monitoring. So let me know if you have any questions on the subject we discussed so far. So I have a question: the unlicensed band can cause interference with other signals. So obviously, unlicensed bands can cause interference with other signals, but the LoRaWAN link layer will take care of the interference, and uh, it will pass on only the LoRa-based frames to the uplink, and our modulation transceivers also are capable of ignoring the other frequencies as well, or other frequencies as well as at the same frequency with not the LoRa based payload. Third question I received is what is the latency of application protocols like DNP3 or DLMS over LoRa? So LoRa, as we discussed, it has got less bandwidth, around 150 kilohertz. So it can transfer around 100 to 50 to 100 Kbps signals. So the latency would be higher, but even if the latency is higher, the SCSC gateways will take care of the compression and fragmentation of the data. So you will not see a normal DLMS or a DNP3 packet over the LoRa. It will be a compressed packet, and it will also be sent out on a fragmented basis. I guess that's all for the questions. Okay, so okay, one more question. What kind of settings would be required in SCADA side or the heaven side? So SCADA is no longer communicating with the directly on LoRa. It will be through the headend, especially in the architecture which I've shown, uh, which uses the Kalki.io as a front-end gateway. It Kalki.io takes care of the latency and the timeouts on the LoRa network, and SCADA will have its own communication link with Kalki.io over TMP3 or IEC or ICCP. So the SCADA will communicate normally with the Kalki.io, but Kalki will take care of the timeout and the latency of the LoRa network. Okay, so I guess there's no more questions. So yes, we can conclude this session. So if you have any questions, please feel free to mail us. We'll be happy to respond to you back. Uh, thank you. Thank you for your time. We'll meet you in the next session. Thanks.